Hi, my name is Andrew Tremblay, and this is Lab 1 for Physics 2211. In this lab, we were tracking the motion of an object, and we chose a ball of yarn to move across the table. The ball of yarn being our system, and the table being the surroundings. This lab was to track constant motion over time. The main ideas of this lab are Newton's first and second law of motion, kind of stating that object in motion will stay in motion unless another force pushes it to change velocity or speed or direction. As it turns out, because this is a real-world application, there's always going to be some type of unbalanced force, so the graphs won't be exactly perfect in terms of having constant velocity. The observed data was taken by getting a measuring stick, a meter stick, and rolling the yarn right in front of it so we have reference point for our tracker app. And we would use that tracker data and plug it into Excel to get a graph and then use a line of best fit. The line of best fit we got was right here. It was 0.5366 x plus 0.0665. We had a really high R squared value, which means that the line fit really well with the data points. The direction of the velocity is in the positive x direction, and we had it going in no other direction, so it would just be a 1 followed by 2 zeros. We are able to find velocity using this equation by just using the slope, because the slope does describe the change in position over change in time, which is exactly what velocity is. Transferring over into the code section, we plugged in the velocity vector as said before, 0.5366. You see right there. The position vector as well at the initial starting point was about 5 centimeters, so that was plugged in as well. And then the time was changed to 1.6 seconds because that's when our observation ended. In this situation, the ball is moving to the right. In our real world situation, we had it moved to the left. We just chose the left as the positive x direction in our experiment because we had the yarn moving to the left and we wanted to work with positive numbers. So this is correct in terms of what we were doing. And then the observed versus predicted. The predicted is a straight line that is perfectly straight. However, the observed line, as you can see right here, it has a little bit of a change where it kind of looks like it's going faster and slower. The change in velocity can only happen if there's an acceleration. This main principle is that there must be some force acting on it to cause a change in acceleration. There are two forces that could be acting on this. The first one, big one, is friction. That will slow it down. So maybe in this later part, we are having some friction going on. Another part, however, is this part where it's speeding up. This speeding up might be able to be explained by the uneven surface. If we go back to the top, you can see that the ruler kind of starts getting away from the table there, which means that this probably was a little lower than the side it started from, so it might have been speeding up due to gravity. Another potential error on our side is by manually clicking the same point, where we could have caused a few clicks in a row that might have been a little bit off center of the point that we were aiming for. What if? The what if here was if we swap the x plus direction. This wouldn't change too much. It would just change the direction vector to -1. All the slopes and whatnot would remain the same. The only difference being the direction of the velocity and acceleration and so forth. Calculating how many push and shoves. In a perfect world, as described by the question, we can calculate how many pushes and shoves if we know that there's nothing else touching it at any moment or any time. There's no friction, so there can't be any force caused by the table. That's the only contact force it has. The only force acted by the table, though, is normal force and gravity acting in the exact opposite direction in order to completely cancel out, which would be 0 force total.